depending on how these couplings to the scalars are chosen in correlation with the shape of the loop. Okay, the simplest example, the most supersymmetric one, which I'll focus on, is the half VPS Wilson loop. So this is obtained by taking the loop to be an infinite straight line or a circle. The two configurations are related by a conformal transformation. And the scalar coupling is just a constant unit 6 vector. So we can take, for simplicity, just take this straight line on the x0 direction, identify x0 with t, and let's pick the scalar coupling to point in one of the scalar directions, say phi 6. So this is the VPS straight line operator. And similarly, you can consider the circular geometry as well. And this preserves 16 superconformal supercharges, so it's half VPS. For this straight line configuration, the expectation value is trivial, it's just 1. For the circular one, as it is well known, it's non-trivial and famously given by the Gaussian matrix model, as was conjectured long ago by Eriksson, Semenov, Zarembo, Drucker, and Gross, and proved by using localization by Peston. Okay, so the observables I'm going to be interested in are this defines as follows. So take some operators OI in the adjoint of the gauge group, so not single trace gauge invariant operators, and then consider the following expectation value. So it's the trace of the path ordered exponential of a string of this operator insertions inside the Wilson line, and there are Wilson line factors going from one operator to the other, so that the whole configuration is gauge invariant. Okay. So it's a gauge invariant observable. It's the expectation value of some single trace non-local operator, which is built this way. But as we'll see soon, this kind of object have the structure of correlation functions in a one-dimensional CFT. So I'll often just use this notation with double bracket, implicitly remembering that this is defined in this way in terms of the Wilson line. Okay. So, okay, it's also in this definition I'm normalizing by the expectation value of the Wilson loop. This is trivial for the straight line, but it's relevant for the circle where the expectation value is non-trivial. And correlators normalized this way on the line and circle map to each other by conformal transformation, just by simply transforming the straight line to a circle. Yes, so the anomaly is just about the expectation value. The loop operator itself, but not on the correlators. It's similar to like when you consider a CFT on the plane or on a sphere. The free energy on the sphere is non-trivial. You can view that as some kind of anomaly if you want, but the correlation function normalized by the partition function just map in a nice way between plane and sphere. So it's the same here. Okay, so correlators of this kind were considered, well, they are related to small deformations of the Wilson loop, because you can imagine starting with some general Wilson loop and deforming near the half VPS circular one, and that will bring down operators corresponding to the deformations. And this was studied a while ago, briefly in a paper by Polyakov and Richkov in 2000, and later in more detail by Drucker and Kawamoto. And the idea, at least in principle, is that if one knows all these correlation functions on the half VPS Wilson loop, in principle one can reconstruct the expectation value of a more general Wilson loop operator of general shape and general scalar coupling, because all these correlation functions are related to deformations of the, say, the circular or straight Wilson loop. Okay. So to understand a little bit better the structure of these correlators, we can remember the symmetries preserved by the half VPS Wilson loop. So these are easy to see. There is an SO3 rotations in the directions orthogonal to the line. So if we pick the line along time direction, and there are symmetries for rotations in the 1, 2, and 3 directions. That gives an SO3. There is an SO5 rotating the 5 scalars, which don't couple to the Wilson loop. So we chose one scalar that appears in the Wilson loop, and we can rotate the remaining 5. So there is a unbroken SO5 out of the original SO6. And then the one crucial observation is that this configuration also preserves a one-dimensional conformal subgroup of the original four-dimensional conformal group, which is a SL2R, because translations, dilatations, and special conformal transformation leave this line or circle invariant. Okay, so this is a one-dimensional conformal symmetry. And together with the 16 supercharges that are preserved by this operator, this combine into some one-dimensional superconformal group, which is OSP4 slash 4 star slash forward. The star just means that this is some non-compact version of SO4, which is a cell to R cross SO3. Okay. And since this preserves a one-dimensional conformal subgroup of the four-dimensional conformal symmetry, it can be viewed as a conformal defect of the four-dimensional theory, namely just some non-local operator which preserves a subgroup of the conformal symmetry. Okay. Okay, so the operator insertions on the Wilson line can be viewed then as defect operators inserted on this defect, and they can be organized using the one-dimensional conformal symmetry in primaries and descendants. So the primaries will be labeled by their scaling dimensions under SL2R and by representations of SO3 cross SO5. So the quantum number will be a dimension, a spin of SO3, and the representation of SO5. Okay, so their correlation functions are then constrained by the one-dimensional conformal symmetry in the usual way. So the two-point function will be constrained in this way, and the three-point function in this way, where deltas are the scaling dimensions. Now here I'm dropping the double bracket notation, but in all this talk you should remember that what I mean here is always what I defined earlier, the correlation functions of insertions on the Wilson line. Okay, so four-point functions are more non-trivial, as we all know. So in one dimensions, the four-point function is constrained by conformal symmetry to take this form. So unlike higher dimension, is specified by a function of only one variable, because there is only one conformally invariant cross ratio in one dimension, which is this chi defined here. And as usual, we expect that there is some OPE expansion, and this function can be expanded in conformal block. And here the conformal blocks are just these two F1 functions, which are the exactly known they are the exactly known conformal blocks in one dimension. Okay, so as usual in a CFT, once you know this, you can extract the scaling dimensions and the OPE coefficients, and in principle, if you know all the scaling dimensions and OPE coefficients, you've solved the theory. Okay. So this kind of system of correlators on the Wilson line is a simple but yet still quite non-trivial example of a one-dimensional conformal system, which may be suitable for application of bootstrap techniques, for example. And this was already studied in a couple of nice papers by Pedro Liendo and Carlo Meneghelli, and it may be also interesting to apply the more recent new functional introduced by Dallimil and studied also by Paulus and Dallimil to this problem. Okay, and maybe somebody is doing this already. So let's see. Okay, so among all the possible operator insertions, there is a special multiplet of simple kind of insertions, which is called the super displacement multiplet. So this is made of 8 bosonic and 8 fermionic insertions, which form some protected short multiplet of OSP4/4. The bosonic insertions are just the 5 scalars that don't couple to the Wilson loop. So these have dimension 1. It's clear that they have dimension 1 at weak coupling, but they're actually protected by supersymmetry because they belong to this short multiplet. And the other 3 bosonic operators are the displacement, so-called displacement operator, which is essentially the field strength plus this term coming from the scalar coupling. So these are the operators that correspond to deformations of the Wilson loop in the transverse directions. Okay, and they have dimension 2. So the fact that this displacement operator has dimension 2 is a general fact about defect, about one-dimensional defects. But the fact that, that this belongs to a super multiplet where this delta equal 1 scalar is the superconformal primary is special to this case. But the fact that this is protected is a more general fact. Okay. Any questions so far?
How much of what you're going to say is in planar limit?
Almost everything, but I will say something about non-planar corrections. But so far I didn't assume, what I'm discussing here, I didn't assume planar limit. Okay, so 2-point functions of these operators are actually completely known because, well, the dimension is fixed, and also the normalization of these 2-point functions can be fixed by localization. As I will review later, these operators can be actually completely captured by localization. So I wrote here the explicit expressions. These functions are related to the so-called Bremsstrahlung function, which is this ratio of Bessel functions. And I'll come back to this briefly later. 3-point functions, if we just look at this multiplet, are trivial by symmetries, at least if we look at bosonic operators. So the next thing to look at is 4-point functions. So these are much more non-trivial. At weak coupling, they are known up to 1-loop order. They were recently computed explicitly in a paper by Shota and Kiryu. At strong coupling, they can be computed using the ADS2 worksheet, which is dual to this Wilson loop. So this is the calculation that we first did in a paper with Radi in the summer of 2017. So I'm just going to very briefly review this. I also talked about this in other talks that you may have seen. So let me just very briefly remember the general dictionary for Wilson loops. So in ADS-CFT, the Wilson loop is dual to a minimal string surface ending on the loop at the boundary. And the expectation value of the Wilson loop is given by the string partition function with the boundary conditions that specify that this surface should end on that loop. Okay, so in the leading strong coupling result, which is a classical limit on the string side, this just reduces to the exponential of the regularized area. But this, of course, this captures also quantum corrections in principle. Okay, so I'll focus mainly on the bosonic part of the string action. And it will be convenient to just use the Nambu-Goto action. So if we just use the Poincare patch coordinates, this is the Nambu-Goto action for ADS5 cross S5, where this is just the Poincare metric. Z is the holographic direction. XR are the 4 direction of the boundary. And this is a particular metric which will be useful for S5. So Y are just 5 coordinates on S5, and this is the conformally flat form of the metric on S5. So the index A here runs from 1 to 5. The index R can be split into 0 and I, where I runs from 1 to 3. And 0 will be the direction where I put the Wilson line. Okay, so the minimal surface, which is relevant for the straight Wilson line, is very easy to guess and to check that it's the correct solution to the equation of motion. It's just a long stretch string, so which ends on the line at the boundary. So the worksheet is just given by this simple solution. If we denote S and T, the worksheet coordinates is just Z equal S and X0 equal T, and everything else to 0. So this is just an ADS2 in Poincare coordinates embedded inside ADS5. The induced metric is just this, which is ADS2 induced metric. So you just take the ADS5 cross S5 metric and specialize to this. It gives an ADS2, as is well known, or the same, yes. Sorry, what S? What is S? No, so the operator couples to one scalar, right? So that means that the scalar coupling is just a constant unit vector. So it just means that we pick a point on the S5. So it's a solution which sits at a point on S5. In this coordinate, sitting at a point on S5 just means that Y is a constant. We could take, so we can take Y equals 0, which means the north pole, say, of the sphere.
But this will affect one loop correction.
Well, this is the classical solution.
Yeah, yeah. If you want to expand, you
Yeah, sure. I'm just talking about.
which level you see the difference between the Wilson line and super?
Oh, I'll come back to that, I hope, at the end of the talk. So far, I'm discussing the half-APS Wilson line, which couples to a scalar. Then it corresponds to this solution, which sits at a point, and the fluctuations that you will consider when you consider quantum corrections have Dirichlet boundary conditions. So they just fix this point, and the fluctuations vanish at the boundary. Okay. Similarly, we can do the circular one, which is just a conformal transformation of this. And we just, in this case, get a disk, and we get the hyperbolic two-dimensional disk. Okay? Sorry. Okay, so this minimal surface is just an ADS2 sitting at a point on S5, as we discussed. It's easy to see that it preserves exactly the same symmetries of the boundary operator that we expect. The SL2R is, of course, realized here as the isometry of the ADS2 worksheet. And the SO3 cross SO5 are the rotations of the 8 transverse coordinates to the worksheet. So there are 3 transverse coordinates in ADS5 and 5 transverse coordinates in S5. Okay, and by expanding this sigma model action around this solution, we can study the fluctuations of this worksheet. Okay, and the idea is that the fluctuations of this worksheet will be related to correlation functions of insertions on the Wilson loop. Okay, so to do the you just do the expansion around that solution. What you find from to do this is convenient to use a static gauge. So we work with Nambogoto action and choose static gauge where x0 and z are identified with the worksheet coordinates, and then let the transverse coordinates fluctuate. So what we get if we do this is just simply, at least the level of perturbative expansion, we get some action for a collection of fields propagating in ADS2 that will interact in some way dictated by the Nambogoto action. Okay, so I'm omitting all the fermions. I'm just discussing the bosonic fields. But so these are the 8 bosonic fields. There are 3 x's and 5 y's. X's are the fluctuations inside ADS5 and y's inside S5. Okay, so this is the quadratic Lagrangian. These are 4-point interactions, and so on. You can go on. Okay, so from the quadratic Lagrangian, we can read off the spectrum. Now let's just view this as some field theory in some ADS2. We can read off the mass spectrum by just looking at the Lagrangian. So we see that the sphere fluctuations are massless, and the ADS fluctuations have mass square equal 2. And then we can just apply the usual ADS CFT logic to map this mass spectrum to some dimensions at the boundary of ADS2. So in this case, the boundary is one-dimensional, so the relation delta delta minus 1 equal m square will give us, of course, what we expect. The 5 fluctuations on the sphere have delta equal to 1, and they are dual to the insertions of these protected scalars, which transforms in the same representation. So the 5 scalars that don't couple to the Wilson loop. And xi, which mass square equal 2, as delta equal to 2, that's dual to the displacement operator at the boundary. Okay. Okay. For m square equal to 0, you can actually ask why I don't choose the other solution. So there are 2 solutions, delta equal to 0 and delta equal to 1. Actually, the other solution is also relevant, but that's relevant for the problem of the non-supersymmetric Wilson loop. So it corresponds to taking the other boundary, choice of boundary conditions, not Dirichlet, but Neumann. Delta equals 0 is not right, as we'll see, but classically, it's essentially delta equal to 0. Okay. Okay, so now, after we identify the spectrum and we know we just have a field, essentially some field theory in ADS2, we can use that with the usual ADS CFT dictionary and compute correlation functions from it. So we can use the 4-point vertex to compute a boundary 4-point function of dual operators. So this is just a picture, a schematic picture of what's going on, at least at 3 level. So we have this worksheet, ADS2 worksheet. We have some boundary insertions. They are dual to some fields propagating on this ADS2 worksheet, and they interact at some point, and we compute the corresponding Witten diagram. Okay, so in Witten diagram notation, this would be just a contact interaction of this type. There are no exchanges just because of the structure of the Nambogoto action. There are no cubic vertices for this kind of fluctuations that I'm considering, which just follows from symmetry. Yes, so this propagator is the ADS2 propagator, is whatever follows from working with this ADS2 theory. We have some ADS2 fields. We choose the usual boundary conditions that correspond to inserting some operator at the boundary of this space. And then we compute the boundary correlation function following the usual dictionary. Okay. So technically, this looks very similar to the usual Witten diagram calculations that people do in supergravity in ADS5 cross S5, but the interpretation is quite different. So here we are, in the supergravity case, one is computing correlation function of single trace operators, which are dual to some protected closed string states, which are described by supergravity. Here we are not, here it's different. What we are computing are just correlation of insertions of operator inside the Wilson line. We just have some single trace object, single trace no local object, which is described by an open string and its fluctuations. So the correlation functions we are computing here are obtained not from supergravity, but from the actual worksheet theory. And the expansion parameter is not 1/n squared, as is the usual correlation function of single trace operator, but it's 1/root lambda. It's just the coupling of the string worksheet action. And n in this discussion is strictly infinity. Okay, so these correlation functions are not suppressed by n. The coupling is 1/root lambda. So technically, you do the same calculation, but the interpretation of what you're computing is quite different from the usual supergravity story. Okay. Any questions about this?
Well, still, if you start from supergravity, at some experiment like we can have, you can introduce 1/n squared dependence.
Well, 1/n squared dependence will come from higher genius corrections of this worksheet. So that's.
No, I'm thinking about supergravity calculation.
But supergravity doesn't describe this sector. So this we really need some open string ending on the boundary, and we are studying the dynamics of that. Okay. Okay, I'm not going to go to the details of how you do the calculation, but if you have seen calculations of Witten diagrams, it's just the same. You just, it's very simple because it's just a contact interaction, so it's just some kind of D function. And so here I'm just flashing what the result looks like for the correlation function of 4 of this sphere insertions. To package the result in a convenient way without carrying all the SO5 indices, it's convenient to contract these y's by some auxiliary polarization, which is taken to be null. And then the correlation function is some prefactor, which is fixed, and a function of the cross ratio and 2 R-symmetry cross ratios, which are these ratios of products of these polarizations. And there are 3 functions here. The way it's written is because you can decompose these into singlet, symmetric traceless, and anti-symmetric channels according to the SO5. That's why it's written in this way. Okay? And just to give you an idea of what you actually get pretty simple functions because these are the functions where the dimension is 1. So these are simple elementary functions in 1 dimension. This is what you get explicitly, just a combination of terms involving logs and rational functions. Okay? And once you have this, you can use the OPE expansion to extract information about the operators that appear in the OPE of this external scalars that we are computing the 4-point function of. Okay. So, for example, well, as a check, you can, for example, look at the symmetric traceless channel and realize that at the lowest level you have some. Well, okay. Let me just review this briefly in case. It's not familiar. So the way you extract, for example, anomalous dimensions is by looking at logarithmic terms in the expansion in small cross ratio, right? Because those logarithmic terms, if you look at the general expansion, OPE expansion corresponds to the perturbative expansion of anomalous dimensions. So by looking at the logs in the small chi expansion, you can extract anomalous dimensions. And if you look at the symmetric traceless channel, you can see, for example, that there is a protected operator with delta equal to 2, which doesn't have an anomalous dimension. So this is like a symmetric traceless product of the scalars. And this turns out to be a protected operator. It also sits in some short multiplet of OSP4 */4, and it's in some sense analogous to the usual chiral primaries that we have in the closed string sector. There we have symmetric traceless representation of SO6. Here we have symmetric traceless representation of SO5. So this is just one example of a whole tower of protected operators which are built out of symmetric traceless products of phi's and have delta equal j, where j is the number of scalars. Okay, I'll come back to those kind of operators later because we will see that they can be described by localization. Their correlation functions can be obtained by localization. Okay, now maybe more interestingly, in the singlet channel, we can see that there is there are unprotected operators. In particular, the lowest lying one, it's a scalar singlet with dimension, 2, which is like the classical dimension of product of two y's, which is dual to the product of two phi's. And then there is a correction which is extracted by looking at the log in these terms, and that correction is -5/√λ. Okay, so from this 4-point function, we can extract the scaling dimension of this unprotected singlet operator, which appear in the OPE. So what is the interpretation of this on the gauge theory side? So if we think back at weak coupling, there we know that the lowest dimension SO5 singlet, which is unprotected, is just phi6, the scalar which appears in the Wilson loop exponent. That operator is not protected, and it has an anomalous dimension. Its anomalous dimension actually was computed long ago by Aldaim, Aldacena, and also later the result was recovered by Polchinski and Sully. So they computed explicitly in perturbation theory. The dimension of that insertion on the straight Wilson line or circular is 1 plus λ/4π². Okay. Now it seems natural to expect that when going from weak to strong coupling, the lowest dimension unprotected singlet should smoothly connect to the lowest dimension unprotected singlet at strong coupling. But that operator is just this two-particle bound state that we found on the worksheet in the worksheet calculation, this product of y's. So it's natural to identify that as the strong coupling counterpart of this phi6 insertion. Okay.
So you do phi6 out of the scalars which are orthogonal to 6.
It's a bit unusual, but it's not inconsistent. If you actually think about just solving, using embedding coordinates for the sphere, then you can express y6 in terms of the other, and y6 is essentially two leading order related to this. Okay. Right. So even though this kind of operators look a little bit similar to what people call double trace operator in the usual story of closed string correlation functions, they are not really double trace operators. So everything here is single trace. So this is allowed to mix. I mean, this interpretation is not inconsistent. It's possible that what you call phi6 at weak coupling smoothly connects to this kind of bound state, which has the same quantum numbers, and it's the lowest operator with these quantum numbers that you find a strong coupling.
If you literally compute this operator at weak coupling,
It's 2 plus some correction. So that operator will probably connect to something above this. I'm not sure to what, but some operator which is a singlet but with higher dimension than this. It could be y with extra derivatives.
so one is 2 minus,
The other, it could go to 4.
but
4.
go up and then down.
It could. I'm not proving this. I'm just saying that it's a natural expectation that this might be the right interpretation for this bound state at strong coupling. Okay. Okay, so here giving you a picture. So the fact that this is 1 plus λ/4π² at weak coupling, so it has 1 plus a positive correction, is also consistent with this possibility of a smooth interpolation between this at weak coupling and this at strong coupling. Okay, this is just a function that I cooked up. Of course, I don't know the function, but the behavior here and here is consistent with such a function, which starts at 1 plus something and goes to 2 minus something. Okay? Okay, so maybe using integrability or maybe bootstrap method, this kind of scaling dimension could be constrained or maybe even found exactly. So we'll know soon. So yeah, so we'll see. Okay. Okay, so now let me now move on to using localization to describe some of the data in these defect correlators. So to use localization, we have to map the straight line, which I was using so far, to the circle. So at the level of correlators, this mapping is simple. You basically just map, you do the mapping between line and circle, and essentially distances on the line are mapped to distances on the circle in this way. T12 is mapped to 2 sine tau 1 over 2, where tau are now coordinates on the circle from 0 to 2 pi. Okay, and similarly for 4-point function, similar mapping applies, where the conformal invariant cross ratio now has this form. Okay. Okay. So as I said before, it's to keep in mind that the expectation value of the circular Wilson loop is non-zero, is given by this expression, and we are, when mapping, relating these correlators on the line to the circle, we have to normalize by this when we are on the circle side. Okay. To actually use localization, we have to slightly generalize the system and consider a family of operators which preserve less supersymmetry, which are 1/8 BPS operators, which are defined for arbitrary contours on a two-sphere. Okay, I'm not going to review the whole construction, but what you can do is consider operators which, Wilson loop operators, which are defined on any curve on some two-sphere inside your R4, and they are coupled to 3 of the scalars in a way which is prescribed by whatever contour you're choosing. So explicitly, very explicitly, these are the operators. So basically, it just means that you have to choose a very special type of scalar coupling which is correlated with the choice of curve. Okay? And I mean, it's not obvious from what I wrote down here that this is supersymmetric, but you can prove that it's supersymmetric for arbitrary contour, and it preserves 1/8 of the supersymmetry. Okay, so the half EPS circular one is contained in this general family as a special case. If you just take the equator of the S2, then this just reduces to the half EPS Wilson loop, circular Wilson loop, which couples to a single scalar. I'm slightly changing notations here because I'm following the original literature, but so by doing that, say if you choose the equator at x3 equals 0 in Cartesian coordinate, you get an operator which maps to phi 3. This is what I was calling phi 6 before. It doesn't matter. So I'm just relabeling the name of the scalars a little bit. So it was conjectured in a paper by myself, Drucker, and others in 2007 that this kind of Wilson loops are captured by two-dimensional Yang-Mills theory, and this was proved later, well, almost essentially best enough, some technical details that were not worked out completely, that it was worked out by localization that this is correct, essentially, although the proof is not fully complete. But if we accept this map to two-dimensional Yang-Mills, it implies a very simple fact about the expectation values. Because of the fact that 2D Yang-Mills is invariant under area-preserving diffeomorphism, this localization map implies that the Wilson loop expectation value only depends on the area of these loops and not on precise shape. And in particular, for any arbitrary operator of this kind, the expectation value is just given by the same Bessel function that you have for the half EPS Wilson loop, but with a rescaled coupling constant, where the rescaling is dependent on the area of this loop that you choose. Okay, so in these conventions, the half EPS Wilson loop would correspond to A equal 2 pi. So that's an equator, and the area is half of the sphere. Okay. Okay. More generally, you can show that there is a larger class of operators that preserve all the same supersymmetries and are captured by localization, which is not just Wilson loops. So you can put any number of Wilson loops on the two-sphere, but you can also insert any number of certain kind of local operators on the sphere. And these local operators, OJ, are essentially chiral primaries, but they are chosen in a way that the RCM direction is correlated with the insertion point. Okay, so these are the operators that you can consider. I'm using the Cartesian coordinates where the sphere is given by this. So this is just some kind of chiral primary combination, because you can view this as some null vector dot phi. It's null because x squared 1, and then there's I here. Okay. So these operators can be inserted on the sphere or inside the Wilson loop. It doesn't matter. They all preserve the same supersymmetry. Okay. So this kind of operators were actually constructed before this application to Wilson loops by Drucker and Plewka, who also argued that because of this particular way that you choose them, their correlation functions are position independent. You can just show that by supersymmetry. This construction is in the kind of similar spirit to what Rastelli and collaborators have been doing with the chiral algebra. There you get a subsector of holomorphic correlators. Here you get position-independent correlators. But the idea is the same. You still consider some position-dependent combination of scalars. Yes?
But the method was also coupling.
In which case? Here? Yeah, this here is all. Here, the correlation functions of local operators by themselves is coupling independent. It becomes more interesting when you also have Wilson loops and you insert these operators inside Wilson loops. Okay, so they are position independent. In the localization map, you can understand this because you can show that this particular combinations of scalars maps to the Hodge dual of the two-dimensional Yang-Mills field strength, and that has also the property that its correlation functions are position independent. It just follows essentially from the equations of motion into the Yang-Mills. Okay. So now just focusing on the case where we inserted this on the circular Wilson line, basically it just means that the operator that we can insert is some kind of combination of scalars where the particular combination depends on the point on the loop where we insert it. Okay, so just specializing this general case to the axis being on the equator, on the circular Wilson loop, it means that we consider this kind of operators. Okay, and so you find a subsector of this defect correlators on the Wilson loop, which are completely position independent. Okay? And they are also non-trivial functions of couplings, which are computable by localization. Okay. Any questions so far? Okay. So even though we look at these topological operators, one observation is that if we think about 2-point and 3-point functions of this, like the general physical chiral primaries insertions inside the Wilson loop, those are fixed, completely fixed by conformal symmetry and R-symmetry up to functions of coupling. So specializing to this topological subsector, we can still reconstruct the full physical structure constants for these operators. But just because it's completely fixed by symmetry, it doesn't matter if we choose these polarizations to be this special kind of position independent. Okay? Of course, this is not true for higher point functions, but still the result for the topological correlators will give some constraint for the general higher point functions of the physical operators. Okay? So how do we actually do this from localization? I don't have time, I think, to discuss the whole construction, but so it's easy to understand what to do in the case of insertions of single powers of these fields, because they are mapped to the Yang-Mills field strength, and because of the area preserving invariance of 2D Yang-Mills, you can argue that insertions of 2D Yang-Mills field strength on the Wilson loop are related to derivatives with respect to area of the Wilson loop expectation value. So inserting any number of these operators somewhere on the Wilson loop can be obtained by just taking L derivatives of the Wilson loop expectation value with respect to area. So this inserts L operators inside the Wilson loop at separate points. Doesn't matter which points, but separate points. So for the 2-point function, for example, you can get in this way immediately the Bremsstrahlung function. You just take the Wilson loop expectation value of the log, take two derivatives with respect to area, and you get this ratio of I2 and I1. Okay. For 4-point function, you can do the same. You take 4 area derivatives, you get this function of coupling, and you can check if you take that kind of complicated looking result that I flashed before for the 4-point function of scalar insertions, and you map it to the circle, and then choose the particular polarizations corresponding to these topological operators, you can check that it precisely matches the strong coupling limit of this. Okay, so it's a non-trivial check. So what about the more general operators, which are products? So here one needs to understand how to precisely define these composite operators, which are products of these fields at a single point. So this should be normal ordered operators, which have 0 1-point functions and orthogonal 2-point functions with everything else. So the way to do this is, again, to start with this L area derivatives, where we have the L operators on the line, and then use the fact that the operators are position independent to bring the operators together at one point, and then use the OPE to write that product in terms of the actual normal order operators that you want to find, plus lower length operators which are produced in the OPE. So for example, in the case of a length 2 operator, you bring two phi's together and then say that that is equal to the actual normal order composite operator phi squared that you want, plus lower order terms. Now in practice, this can be done systematically using Gram-Schmidt orthogonalization procedure. So what we are doing is just constructing a basis of normal ordered orthogonal operators, which are linear combinations of product of these single letter insertions, starting at length L and lower length. So it's basically an orthogonalization procedure starting with the basis of non-orthogonal operators, which is the identity, phi, phi phi, phi phi phi, and so on. Okay? And let me just say that, so I didn't say this very explicitly so far, but the procedure as I described it here is actually only valid in the planar limit, where when we consider OPE of this kind, we only produce operators which are inside the the trace of the Wilson loop. At non-planar level, you actually have to also worry about other kind of operators, more general defect operators, which are in general operators of this kind, where you have insertions inside the Wilson loop trace, and traces, single traces, also inserted at some point on the loop, but attached. You know, the color structure is such that you have kind of a multi-trace object. Okay. So if you want to do this at non-planar level, you have to include these operators in the Gram-Schmidt procedure, and it becomes more complicated, but it can be done. Okay. So, but now staying at the planar level, the result is relatively simple. It looks a little bit complicated, but what this Gram-Schmidt procedure gives you is just an explicit expression for what these normal ordered operators are in terms of derivative of Wilson loops with respect to area. So this is just a determinant. DL is the determinant of this matrix. W is the expectation value, and this number just means how many area derivatives you take. Okay. So for example, the 2-point function is given just by a ratio of determinants of this kind. Okay. You can get explicit expression for any of these correlation functions. Just to give you an idea of what they look like, well, because you just start with these Bessel functions, you'll get combinations of Bessel functions and ratios involving Bessel functions. So these are 2-point functions, these are 3-point functions, and so on. Okay. It's also interesting to write down in a nicer way the structure of these correlation functions in the planar limit. So you can use the fact that the Wilson loop expectation value can be written as some contour integral, where this is measure given here, and this parameter, so G is just root lambda over 4 pi, and this small a is just related to the area of the Wilson loop. Okay, and so this, if you do this contour integral, you just get the Bessel function. But this is a convenient way to write the result, in which you can take the area derivatives in a simple way. They're just given by insertion of these monomials inside this contour integral. Okay, and then if you do this, what you realize is that the correlation functions of any numbers of these operators can be written as simple looking contour integral of a product of some polynomials, QL, which are polynomials in this variable g x minus 1 over x. Okay, so you map this general correlation function in this subsector to just some integral of a product of polynomials. Okay, and in particular from this expression, you can, for example, recover the localization, sorry, the integrability result for the generalized Bremsstrahlung that Collier and friends derived. And actually the comparison is quite direct in the sense that these functions, these polynomials here that we get from localization turn out to be directly related to the Q functions that appear in the quantum spectral curve approach. And because we find that integrals of these Q functions give correlation functions, this kind of hints at the possibility that the quantum spectral curve is useful not just for the spectrum, but also for correlation functions. And the similar observation was made in a related but slightly different setup in a paper by Collier, Cavaglia, and Levkovich-Maziluk last year. Okay, much time left. Okay, one can also check these results at weak and strong coupling. You can, in that case, this kind of integral become manageable. These polynomials actually reduce to classical orthogonal polynomials. At weak coupling, they reduce to Chebyshev. At strong coupling, they reduce to Hermite. And you can evaluate this at weak and strong coupling, and you can verify that, well, we have verified to the first two orders in perturbation theory, both at weak and strong coupling, that they match the known perturbative results. On the string theory side, what you need to do is just a slight generalization of what I was describing earlier. What you are computing is actually a correlation function of products of string fluctuations. So you take a product of, say, L of this sphere coordinates, and you can compute a correlation function of these products and bring the points to the boundary and compute the corresponding Witten diagrams. So diagrammatically, these are the kind of calculations you can do with the ADS2 worksheet theory, where now instead of a single scalar insertion, we have some composite insertion at the boundary. So this will be the case of L equal 4. This will be the leading term in the 4-point function, which is just generalized free fields in ADS2, and this is the correction using the 4-point vertex. And this is for 3-point functions. Okay, so you can do these calculations and verify that they exactly match localization. Okay, let me very briefly just go over this. So far I was focusing just on the correlation functions of insertions on the Wilson loop. So just correlation functions operators on the defect. But in a defect CFT, you can compute more general quantities, like so-called bulk defect correlators, which are correlation functions of, in general, defect operators inserted on the defect and some operators away from the defect. So in this context, this would be like a correlation function of some single trace operator inserted somewhere on R4 and insertions on the Wilson line. So on the string theory side, this would correspond now to some kind of mixed closed string, open string amplitude, where we have the ADS2 worksheet. We have some, we have these insertions at the boundary, which is dual to some fluctuations propagating ADS2. We have a vertex operator, which is dual to the closed string operator that we insert away from the defect. And this is just an ADS5 bulk to boundary propagator, connecting the insertion point to the vertex operator. So you can compute this from the string theory side. And you can also derive exact results for these correlators from localization. I'm not going to describe the full procedure, but what you get in the end, at least at leading order at large n, is again a very simple expression in terms of the same Q functions. So here is, for example, the correlation function of one single trace operator of this particular kind, which is captured by localization and insertions on the Wilson line. It's given again by a contour integral of a product of Q functions times some function Bj, which is a simple function here, which essentially, at least intuitively, plays the same role as this insertion of vertex operator on the open string worksheet. Okay? And to actually obtain these results, it's important to take into account the effect of mixing with these general multitrace operators that I was mentioning before. And doing this, one can also obtain non-planar one-over-n corrections to just the purely defect correlators. You can again write those in terms of integrals of Q functions, but it's a little bit more complicated, and I didn't write the result here, but it's in this paper that I wrote with Shota last November. Okay. Any questions about this before I slightly change topic?
So those correlators which give in the functions,
Mhm.
that was a special combination.
Yes, so they don't depend on the they are numbers. Everything is just a number.
Possible to deform a bit from there so that you can drop some structure outside. Yes.
Well, then in integrability, I'm sure, but in localization, I wouldn't know how to do that.
Yeah, right, but like in some big counterpart, but see how to modify the structure outside.
Yeah, I mean, I didn't look into that, but yes, it should be possible. You may not be able to obtain. Yeah. Mm-hmm. Yeah, but I think even working out the integrability description of this kind of correlators has not been worked out much as far as I know. Yeah. Yeah, so. Yeah. Sorry?
The Q functions for the vacuum, or do they contain some variables?
What's the Q function for the which is relevant for this Wilson loop?
Because you said this Q is the Q function of quantum spectrum, but the operator they consider is kind of protected, you didn't say?
Yeah, it's protected. The operator is protected, but the structure constants are still non-trivial. So this gives some non-trivial functions of coupling, which are the structure constants, say, in the 3-point functions of these operators. Okay, I don't have much time left, but let me, in the last part of the talk, discuss a little bit about the non-supersymmetric Wilson loop. So far I was discussing the Maldacena-Wilson loop, but of course it's very natural to just ask about the usual Wilson loop that we have in any gauge theory, just the standard one. For a smooth contour, there are no logarithmic divergences in the expectation value of this operator. So well, there are divergences when you have cusps, but if we just restrict to smooth contours, then there are no logarithmic divergences. And so again, when the contour is a line or a circle, this operator should preserve again an SL2R conformal symmetry, which doesn't get spoiled because there are no logarithmic divergences if you compute the expectation value in perturbation theory. So by the same logic that I was describing before, you can consider correlation functions of operator insertions on this operator, and they will define some other defect CFT with a different symmetry. It's a non-supersymmetric defect CFT with symmetry SL2R cross SO6. You now have SO6 because this doesn't couple to any scalar, so it doesn't break the SO6 symmetry of the gauge theory. Okay, it's actually it's instructive to consider a kind of more general interpolating operator between the usual Wilson loop and the Maldacena-Wilson loop by adding this coupling constant zeta, multiplying a scalar. Okay. Now, if you consider now this operator with the arbitrary zeta, there are actually logarithmic divergences in the expectation value, which can be reabsorbed in renormalization of this zeta, and then zeta gets a non-trivial beta function. This can be computed in perturbation theory. It was computed again long ago by Aldheim, Maldacena, and Polchinski and Sully. And what you find is that the beta function is given by this expression to leading ordered weak coupling. So lambda is just a 't Hooft coupling of the gauge theory, and zeta is this coupling on the Wilson loop. So you see from here that there are two conformal fixed points, which are zeta equals 0, which is just the ordinary Wilson loop, and zeta equal 1, which is the supersymmetric half-VPS Wilson loop. So this operator can be viewed as defining some kind of RG flow between these two operators. And from this beta function, you can read off what are the dimensions of this perturbing operator phi 6 near these two fixed points. The dimension at the fixed point 1 is the one I already showed before. It's 1 plus lambda over 4 pi square. The dimension at near z equals 0 is 1 minus lambda over 8 pi square. So phi 6 near the zeta equals 0 fixed point is a slightly relevant operator. So you can view this zeta coupling as defining some defect RG flow between the non-supersymmetric Wilson loop in the UV. So that's like a UV fixed point, and an IR stable fixed point, which is the half EPS Wilson Maldacena Wilson loop. Okay. So it's interesting to about something like F theorem in this situation. So it's natural to view the expectation value of the log of the expectation value of the Wilson loop as some kind of free energy for this one-dimensional defect. So it's natural then, to, if F is log of W, to expect that FUV should be bigger than FIR. Okay? You can try to check this by doing the actual calculation. So you do a direct perturbative calculation of the expectation value. You find this result in terms of zeta. So zeta equal 1. This goes away, and this is the usual expansion of the Bessel function that you may have seen. So for the half EPS Wilson loop, for zeta equals 0, you get this this extra term. But you can check that indeed it's true in this perturbation calculation that the log of the expectation value of the non-supersymmetric Wilson loop is indeed bigger than the log of the expectation value of the half EPS Wilson loop, which is consistent with this idea that there should be some generalized F theorem that applies for RG flows on the defects. Okay, this was actually discussed after we did these calculations in a more general context in a paper by Nishioka and others for more general defects, not just one-dimensional defects. Okay, you can also check this at strong coupling. I didn't discuss yet what is the strong coupling description, but I'm just giving you here what the result is. So for the supersymmetric Wilson loop, in the leading large lambda limit, you get this, where e to the root lambda comes from the exponential of the area of the minimal surface. And this factor comes by counting the number of zero modes. And by thinking about what are the zero modes in the case of the non-supersymmetric one, you can argue that the behavior in that case is this different power. And then again, you can check that the log of this is bigger than the log of that. Again, satisfy the F theorem. Okay, but let me just explain. Okay, that thing is flashing. So that means I don't have much time left. So let me just explain a little bit what is the dual of the ordinary Wilson loop at strong coupling. Again, I'm citing Aldheim, Lessin, Polchinski, and Sully many times. They proposed this a while ago, and they proposed that simply what you're supposed to do to describe the ordinary Wilson loop is, again, finding the minimal surface ending on the contour, but then choosing, instead of Dirichlet, Neumann boundary condition on S5. So that means that we don't pick a particular point on the S5, so the worksheet doesn't sit at any specific point. We just use Neumann boundary condition, and then there is some zero mode, or 5 zero modes, which describe the position on the S5, and we are supposed to integrate over that position to recover the SO6 symmetry of the operator. Okay, if you want to do this explicitly, you can write the S5 coordinates in terms of embedding coordinate in the splitting, where NA is just some constant unit vector specifying a position. ZA are fluctuations with Neumann boundary conditions, and then you have to compute correlators of this and integrate over the position to recover, the position on the sphere to recover SO6. For example, yeah.
Does it make sense like that style of worksheet, or it's purely classical?
Well, it's supposed to make sense.
But is it clear how to actually develop systematically?
Yes, yes. You just have to use a different propagator for the S5 fluctuations, which actually I'm writing here. So I'm giving you the simple example, which is like computing the two-point function of these insertions. So now what is natural to identify with the boundary insertions of scalars is directly this embedding coordinates, big Y, which transforms in the same fundamental of SO6, right? So correlation functions of phi's are like correlation functions of Y insertions at the boundary. So this is like how the two-point function would go at leading order. You just expand, and this expectation value now means that you're also supposed to integrate over n, the position on the sphere. So that gives an SO6 invariant result, and then you get this, which comes from the propagator of these fluctuations. And now this propagator is not the one that you would use for the usual calculations with the HPPS Wilson loop. It's a propagator in ADS2, which satisfies Neumann boundary condition. So explicitly it's given by this. The difference between Neumann and Dirichlet is just a choice of relative sign between these two terms, basically. You can think of this as coming from some kind of image charge calculation, right? And then Dirichlet is a minus sign here, and Neumann is plus sign, okay? So the prescription is clear for loops. You just have, use the same action, but you quantize these fluctuations using Neumann boundary conditions, which means that you have a different propagator, and you also have some zero modes that you have to integrate over.
Yeah, that's the fluctuations in ADS, but it's like kind of S5 fluctuations.
No, these are not, these are S5 fluctuations, not ADS. ADS you don't touch, ADS you don't change anything there. It's just S5 that you change Dirichlet to Neumann. Okay. Okay, so from this two-point function, if you take the boundary limit, where you take these 2 points to the boundary, then because now you have this Neumann propagator, this when you send z and z prime to 0, you just get some log. T is the string tension, so you get here something like 1 plus 1 over root lambda log of T12 square. So you can interpret that as the expansion of a conformal two-point function where delta, well, if you work out the numerical coefficient, delta starts as 5 over square root lambda plus correction. So it's kind of 0 in the strict lambda going to infinity limit. That's why before I was saying that delta minus 1 equals 0. You could choose delta equal 1 or delta equal 0 classically. Now, if you actually do the calculation more carefully, the delta equal 0 should be viewed as delta equal 5 over root lambda, which is what you get from using these Neumann propagators. Okay? So now the dimension of this simplest scalar insertion is consistent with a smooth interpolation between 1 and 0 instead of 1 and 2. So it's for this non-supersymmetric loop. It starts from 1 minus lambda over 8 pi square, and it goes to 5 over root lambda plus corrections. Okay. I don't know. Not from localization, not for sure, but integrability and bootstrap should apply here as well. I don't think there is a strong reason to suspect that integrability does not apply for the ordinary Wilson loop in any for superior mills. In fact, there was a recent paper by Correa and others which studied this at one loop level in the gauge theory, and they found that the dilatation operator for insertions on the ordinary Wilson loop is integrable at one loop level. Yeah. Okay, I will not do this, but okay, in practice it's much more complicated than what I did before. You can go ahead and compute 4-point function, for example. It's more complicated for various reasons. One is these logarithmic propagators. The other reason is that the insertions now are actually non-trivial, non-linear composites of the actual fields, because you start with this kind of expansion, and then the actual fields are ZA, and so this is some complicated composite. Okay? It's a little bit like in flat space string theory, we insert like a plane wave e to the I chi x kx, which is not x itself, and then you get a conformal operator, even though x is logarithmic propagator. Here it's a little bit similar, but not quite the same, but you still have to consider some complicated composite insertion, and that gives you conformal correlation functions. So this is what the 4-point function looked like, and I don't want to go to the details, just to let you see that it's quite more complicated than the HPPS case. It involves now more complicated function, Li3 and Li2, in addition to logs.
Is D2 something you don't know?
Oh, thank you. Yeah, D2 is something we don't know. D2, is basically the correction to the dimension of these operators to the next order. So it's 5 over root lambda plus d2 over lambda. So the other complication is that now these insertions are not protected. Before they had exactly delta equal to 1 in the supersymmetric case, and you didn't need to worry about the renormalization of the scaling dimension for the external insertions, but now they are not protected. And when you compute this 4-point function, there is a contribution that comes from that unknown coefficient. Okay. Okay. So I think I'm already out of time. Let me just conclude. So correlation functions on the straight or circular Wilson loop, either symmetric or non-supersymmetric, have the structure of a d=1 conformal system. So it's like a defect CFT. Correlator of the operator insertions at strong coupling can be obtained using the ADS2 worksheet. So it's like an example of ADS2 CFT1, where the ADS2 in this case comes just from expanding the Nambu-Goto action around this classical solution. It will be interesting to see whether there is a manifestation of integrability somehow in the ADS2 amplitudes. Maybe there is some analog of asymmetric factorization that you can see at the level of Witten diagrams. But I'm not sure what's the right way to study this. One obvious guess is that one needs some kind of Mellin space description of these amplitudes. But I think people don't quite know what is a useful way of using Mellin space in one-dimensional CFTs, because what you would need is just a Mellin amplitude, which is a function of a single variable, to map to the fact that the 4-point function is a function of a single variable, and also to the fact that the scattering amplitude in two-dimensional flat space for 4 points are functions of a single Mandelstam variable. But if you just apply the definition of Mellin amplitude that people use in higher dimensional CFT, you just get a function of 2 variables, S and T. And then it's not clear how to interpret that as some kind of scattering amplitude in a 2-dimensional theory. Okay. So I also discussed how for the case of HPPS Wilson loop, we can get various exact results in a topological subsector of these special operator insertions. It may be interesting to understand whether there is a topological subsector of the string theory which captures this. So some kind of simplified version, topological version of ADS CFT, where you just have a subsector which is exactly dual to this subsector of operators captured by localization. Okay, so I described some perturbative results and some exact results by localization. It seems plausible that at least some of the defect CFT data may be fixed exactly using input from integrability, or maybe bootstrap, or maybe both. So I hope this is a simple enough system where we can use all these techniques in conjunction to maybe find an exact solution. Okay, thank you.